Hi, everybody. It is April 30th, and we are starting a new unit. Very exciting. This unit is on gases. Do you know what I'm going to start putting in these boxes? I hope you're thinking particle diagrams. So let's do this as a reminder. A particle diagram is a real simple way to represent what we can't see. These are atoms or molecules. In this case, we've got the solid phase. If I were to draw the liquid phase, I would want to show my particles all filling in the bottom part of this container. And then if I were to draw a particle diagram for gases, we're going to want to show those particles taking up the volume of the container with a lot of distance between the particles. Notice that solids and liquids are considered condensed because the particles are in contact with each other. They really can't be pushed together or more closely together than they are already. Whereas gases actually have a lot of space between them and do take up the volume of a container. And they are said to be compressible because if I wanted to reduce the size of that container, I could make those particles, push them together or compress them a little bit more. Today's lesson is really focusing on, general properties of gases. They are compressible. They also take the shape of the container. And as these particles are in random motion, I could even show it with little arrows, right? Bouncing into each other, bouncing into the walls of the container. They exert what we call pressure. And pressure is force per unit area. So, in attempts to explain the behavior of gases, the kinetic molecular theory was developed. So, please be aware that this is a model. And it's a model for the behavior of ideal gases. And what that means is this theory models the perfect conditions under which gases could behave. The reality is the world is not perfect. So there's deviations from this theory, but it's still a good model. It gives. Another thing we need to be aware of is that the smallest gases, the smallest element, hydrogen, and the second smallest element, helium, they behave the most like ideal gases. So let me give you the four components of the KMT. Gas particles are in continuous random motion, and their collisions are called elastic. And that means, so they randomly move around continuously and collide without any loss of momentum. The second part to the KMT states that gas particles are separated by great distances. And because of that, we could consider their volume negligible. Now, the fact is, gases are made up of atoms, and all atoms have volume. But because there's so much space between these, and the fact that we could compress this down into a much smaller container, we could, under ideal circumstances, say that gas volume is negligible. The third part to the KMT states that gas particles are considered as having no attraction for each other. But in reality, there are intermolecular forces of attraction known as dispersion forces that we learned 2 units ago. The fourth part of the kinetic molecular theory states that reactant gas particles must collide with proper energy and orientation for a reaction to occur. And that's known as collision theory. Okay, so let's kind of talk about some properties of gases. And when we study gases, we like to talk about pressure a lot. I will abbreviate it with a capital P. And pressure refers to gas particles exerting pressure or force per unit area on the walls of their container and other surfaces. There are a number of reference tables that we will be looking at when we study gases. The first one I want to highlight is Table A, Standard Temperature and Pressure, which is abbreviated STP. It references several units of measurement: kilopascals, atmospheres, and millimeters mercury. All of these units with their values are all equivalent to each other, and they are all considered to be standard pressure at sea level. Okay, so how can we measure pressure? We would use a barometer. I'm going to show you a very crude or simple barometer. As shown here, we could have a pan containing liquid mercury, Hg. We would have a closed tube at the top, and it's open to the bottom but submerged below that liquid mercury. And there's a space up here, a vacuum. The atmosphere is exerting pressure, and as it does, it pushes down on the surface of the mercury. When it pushes that mercury down, that mercury rises in this tube. This scale here indicates the air pressure indirectly as it changes the level of the mercury in the tube. So if I had a higher atmospheric pressure, there would be a higher level of mercury in the tube. If I decreased the atmospheric pressure, that mercury would be a little lower in the tube. Okay, so let's switch it up a bit. We're also going to talk a lot about temperature when we talk about gases. And I'm showing you degrees Fahrenheit just because we all, living in the United States, we all relate to these temperatures more so than the other two. So this is just to give you a point of reference, but we know as science folks, we're going to focus on Celsius and Kelvin. A quick reminder from earlier in the year, temperature is in table T, and you can do your conversion back and forth between Celsius and Kelvin there. Okay, so absolute zero. This is the point at which molecular motion completely stops. Well, on the Kelvin scale, if I want to freeze water, it's 273 Kelvin. Notice I am not using the term degrees. These are not degrees, it's just Kelvin. Let's compare. Absolute zero on the Celsius scale is negative 273 degrees Celsius. And water freezes at 0 degrees Celsius. Okay, let's go on to water boiling. In the Kelvin scale, you add 100 kelvins and water boils at 373. At the Celsius scale, hopefully we all know this by now, right? That water boils at 100 degrees Celsius. If you notice, the increments are equivalent here. We're going from 0 to 273 to 373, negative 273 to 0 to 100. The units are the same magnitude. Looking ahead here, let's talk a little bit about phase changes associated with gases. As you can recall, when a gas turns into a liquid, What do we call that? Condensation, thank you. When a liquid changes its phase into a gas, what do we call that? We call that evaporation. Evaporation is always happening, but it could happen at any temperature. We're going to talk about vapor pressure versus vapor. So a vapor refers to the gas phase of a substance that is liquid or solid at room temperature. So I have this container here, closed container of water, okay, actually has water vapor trapped above it. Now, vapor pressure is that pressure exerted by the vapor gas. So what I've drawn here is a closed system, just like this capped jar is a closed system that I've created here. If you think about it, if I left this jar sitting here undisturbed for a year from now, what do you think is going to happen to the level of the water in that jar? If you said nothing's going to happen to it, you would be right. Because even though the water in that jar is constantly evaporating at some rate, the vapor phase of that water is trapped below the top of that container. So there's vapor pressure being exerted above that liquid. And be aware, as the gas molecules of water collide with the liquid surface, they return back to the liquid state. So in a closed system, we have an equilibrium established. And that means that the rate of evaporation is equal to the rate of condensation. Now, if I took the top off of my container, I now have an open system. A year from now, I can assure you there's going to be no liquid left in here. Why? Because the water all escaped in the gas phase and has become part of our atmosphere. So I look forward to our next lessons together on the new unit of gases. Thank you. Have a great day. Bye.